Hi, welcome to Features of the Gaussian or Normal Distribution, Part 2, Probability Bands and the 68, 95, 99.7 rule. So let's say we have some quantity that is a random variable with a probability density given by a Gaussian distribution with mean mu and standard deviation sigma. When we measure the value of this quantity, what is the probability that the result is more than 1 sigma away from mu, or 2 sigma away from mu, or 3 sigma away from mu? For example, let's say that the scores on a standardized test are Gaussian distributed with a mean of mu equals 1000 and a standard deviation of sigma equals 100. If you choose a person who took the test at random, what is the probability that they scored more than 1 sigma away from the average? In other words, less than 900 or greater than 1100. What is the probability that they scored more than 2 sigma away from the average, or 3 sigma? In this video, we'll give the answer to this and similar questions. So many phenomena in science and everyday life are approximately Gaussian distributed, or in other words, normally distributed. It is good to know these results off the top of your head so that you can know how unusual or run-of-the-mill a certain result is. Now, in this video, we will assume that you're a bit familiar with the Gaussian distribution. If you're not, you might want to check out the videos Why the Gaussian, or Normal, Distribution is Important, and Features of the Gaussian, or Normal Distribution Part 1, Mean and Standard Deviation, both of which are available on this channel. These videos, along with others, can be found in the Gaussian Statistics playlist. For all of the plots in this video, we'll use Gaussians which have a mean mu of 0 and standard deviation sigma equal to 1, but the statements we make will be true for any Gaussian. We'll also reference the above standardized test with an average score mu equal to 1000 and a standard deviation sigma equal to 100 to make our statements more concrete. First, let's start with the band that is plus or minus 1 sigma around the mean mu. So here we plot a Gaussian with mu equals 0 and sigma equals 1. So we've shaded in the area under the curve between x equals minus 1 and x equals plus 1. Approximately 68.3% of the time, the observed value of our random variable will fall in this band that is 1 sigma on either side of mu. In the case of a standardized test with mu equal 1000 and sigma equal 100, approximately 68.3% of test takers have scores between 900 and 1100. So next, consider the band ranging from mu minus 2 sigma to mu plus 2 sigma. We represent this on our mu equals 0, sigma equals 1 Gaussian by shading the area under the curve from x equals minus 2 to x equals 2. In approximately 95.4% of cases, a Gaussian distributed random variable will fall in this band. Approximately 95.4% of test takers in our example will have scores between 800 and 1200. Okay, here we show the region within 3 sigma of mu, represented here by the area under the curve for x between minus 3 and plus 3. In about 99.7% of cases, the value will fall in this band. So about 99.7% of test takers in our example would have scores between 700 and 1300. So the above results are useful often enough that they are known as the 68-95-99.7 rule. To summarize, the observed value of a Gaussian distributed random variable will fall 1. Within 1 sigma of mu in approximately 68.3% of instances, 2. Within 2 sigma of mu in approximately 95.4% of cases, and 3. Within 3 sigma of mu in approximately 99.7% of instances. Now we'll look at some other useful bands. While not as frequently useful as the 68-95-99.7 rule results given above, they still come up reasonably often. It's good to know that one can define these other bands and look up the results if necessary. Okay, so here we show the band symmetric around x equals mu, where a Gaussian distributed random variable will fall in 90% of instances. So this band ranges between approximately x equals mu minus 1.64 sigma and x equals mu plus 1.64 sigma. So in our Gaussian distributed test score example, 90% of test takers will have scores between approximately 1000 minus 1.64 times 100, which equals 836, and 1000 plus 1.64 times 100, which equals 1164. The analogous 95% band ranges between approximately mu minus 1.96 sigma and mu plus 1.96 sigma. This is very close to the 2 sigma band defined earlier. The analogous 99% band ranges between approximately mu minus 2.58 sigma and mu plus 2.58 sigma. About 99% of test takers would score between 1000 minus 2.58 times 100, which equals 742, and 1000 plus 2.58 times 100, which equals 1258. So far, we've seen only bands that are symmetric about x equals mu. But sometimes we'll be interested in bands that extend to x equals minus infinity or x equals infinity. Now we'll show a few of those. So here we show the one-sided band extending up from x equals minus infinity, which would contain 90% of observations. It extends up to approximately mu plus 1.28 sigma. In our test score example, 90% of test takers would score below about 1000 plus 1.28 times 100, which equals 1128. As the distribution is symmetric, we could alternatively look at the 90% band ranging from x equals mu minus 1.28 sigma up to x equals plus infinity. 90% of test takers would score above approximately 1000 minus 1.28 times 100, which equals 872. Okay, so the 95% one-sided band is shown here. It ranges from x equals minus infinity up to approximately x equals mu plus 1.64 sigma. So 95% of test takers would score below 1000 plus 100 times 1.64, which is equal to 1164. So you might have noticed that the upper edge of the one-sided 95% band, located at x equals mu plus 1.64 sigma, is at the same place as the upper edge of the two-sided 90% band. So in 5% of cases, the observed value of x will be above mu plus 1.64 sigma. And as the distribution is symmetric, we also know that in 5% of cases, it will be below mu minus 1.64 sigma. So in 95% of cases, the observed value will be below mu plus 1.64 sigma. And in 90% of cases, it will be between mu minus 1.64 sigma and mu plus 1.64 sigma. Okay, finally, we give the one-sided 99% band. It ranges from x equals minus infinity up to approximately x equals mu plus 2.33 sigma. So 99% of test takers would score less than 1,000 plus 100 times 2.33, which equals 1233. Okay, let's summarize. In this video, we've seen the probability for the observed value of a Gaussian distributed random variable to fall in certain ranges, depending on the mean mu and standard deviation sigma of its Gaussian probability density function. We've seen the 68, 95, 99.7 rule and the one-sided and two-sided 90%, 95%, and 99% probability bands. These ideas come in handy in many applications, and they'll show up in other videos on this channel.